Imagine an ant leaving its nest in search of food. It has no map of the ground, no view from above, and no leader telling it where to turn. At first, its path is a sequence of local, uncertain choices. Another ant explores somewhere else. From above, the colony seems to be drawing random lines between the nest and the world. Now one ant finds a breadcrumb. On the way back, it leaves a chemical trace, pheromone. The trace does not command the next ant, it changes the probabilities. At a fork, a stronger trail makes one direction more likely, while chance still allows the colony to explore the other direction. Suppose two routes connect the same nest and the same food. One route has length L short, the other has length L long. Assume, for the moment, that every ant walks at the same average speed, v. The short route ant reaches the food and returns before the long route ant completes the same journey. For route I, one outward trip covers Li. The return covers another Li. The total distance is therefore 2 Li. Time is distance divided by speed, so the round-trip time is Ti equals 2 Li divided by v. A shorter route means a shorter clock cycle. Assume that every successful round trip adds the same small pheromone amount, Q. The deposition rate is the amount per cycle divided by the cycle time. So Ri equals Q divided by Ti. Substituting the time we just derived gives QV divided by 2 Li. Under these assumptions, reinforcement rate is inversely proportional to route length. But pheromone also evaporates. During one small time step, part of the old trail disappears, while returning ants add a fresh amount. We can write this as tau at the next time equals 1 minus rho times the old tau plus the new deposit. A trail survives only when it is refreshed fast enough. We can turn trail strength into a route probability. Raise each trail strength to a sensitivity power, then divide by the sum over all routes. A small exploration floor keeps an unmarked path possible. The result is not a deterministic order. It is a probability distribution continuously changed by experience. What has the colony done? No ant has measured every route, yet many uncertain samples, accumulated through local feedback, have produced a useful estimate. Short, successful routes are refreshed quickly. Long routes are more exposed to evaporation. This is distributed statistical inference, although it does not guarantee the best path in every environment. Now we can build a careful bridge to a neural network. Let an ant represent one information-bearing sample. Let a trail represent a connection whose influence can change. Let pheromone strength suggest accumulated preference, and let food represent a useful outcome. These roles are analogous. They are not physically identical. In a real nervous system, a neuron is already a living cell. A crossing between two lines does not create one. Signals arrive through synapses, the cell integrates their effects, and activity can change synaptic efficacy. Timing-dependent plasticity is one biological example, but this local biological process is not the same algorithm as backpropagation. An artificial neuron begins with numbers. Input activation A1 arrives through a connection with weight W1. The same happens for a 2 and a 3. The node multiplies each activation by its weight, adds the products, and adds a bias. The result is Z equals W1 A1 plus W2 A2 plus W3 A3 plus B. The weighted sum is then passed through an activation function. Here we use a sigmoid. Very negative inputs produce values near 0. Very positive inputs produce values near 1. Values in between produce graded responses. The output activation is sigma of Z, and it becomes an input to the next layer. Connect many such units, and we obtain a network. Our visible model has 5 measured inputs, 6 units in a first hidden layer, 3 units in a deeper hidden layer, and 1 output. Every edge thickness comes from an actual numerical weight. Every glowing node shows an activation calculated by this model. The model receives deliberately simple measurements: sweetness, aroma, softness, and organic pattern and hardness. Bread, fruit, sugar, and seeds provide food examples. Pebbles, plastic, and metal provide non-food examples. This is a synthetic teaching problem, not a realistic model of animal perception. At the beginning, the weights are random. A fruit sample moves forward, but the output may be uncertain or wrong. Call the output y hat and the correct target y. A simple loss is 1/2 times the square of their difference. The loss is one number measuring how badly this prediction missed this target. To improve a weight, we ask how a tiny change in that weight would change the loss. The chain rule follows the dependencies backward. Loss depends on y hat depends on z, and z depends on the weight. Multiplying those three local derivatives gives the derivative of the loss with respect to that weight. The magenta motion travels backward through the drawing because derivatives are being assigned through a computational graph. It is not a biological electrical spike running backward through an axon. Once the gradient is known, the update subtracts a small learning rate times that gradient. The weight moves in the direction that reduces this error. Now the same fruit sample moves forward again. The output is slightly closer to 1, and the loss is smaller. Repeating this process over many varied examples changes many weights together. The network is not memorizing one route. It is adjusting a distributed system of influences so that useful regularities are shared across examples. Unused connections can also be encouraged to shrink through weight decay. This is separate from backpropagation. The gradient says how the current prediction error depends on a weight. Decay gently pulls weights toward 0. Of the two mechanisms, decay is the closer visual relative of an evaporating pheromone trail. Look now at the first hidden layer. No unit is born with the label sweetness, bread, or food. Each unit combines several measured cues with positive and negative weights. Across training, different mixtures become useful. The layer replaces 5 raw readings with a new pattern of 6 responses. The deeper layer combines those combinations. Bread, fruit, sugar, and seeds remain different objects, but several of their first layer patterns lead to related deeper patterns. The network is beginning to preserve what is useful for the task while discarding distinctions that do not help decide food versus not food. We can see this compression in a representation map. Each dot is one experience. At the input, the samples are separated by many surface details. After one hidden transformation, some useful structure appears. Deeper inside, food examples gather into a shared region while non-food examples move elsewhere. The concept is a distributed geometry, not one magic food neuron. With noisy evidence, the answer need not be exactly 0 or 1. The output can be read as an estimated probability of food given the measured cues. This is why statistical inference is a useful language for both brains and learning systems. It is a model of how uncertain evidence may be combined, not a claim that every brain process is this network. Depth can support abstraction because later layers can combine patterns already built by earlier layers. But depth alone guarantees nothing. The data, objective, architecture, and learning process must make a useful hierarchy possible. When they do, many experiences can be compressed into an internal structure that supports a new prediction. The colony and the network now reveal the same broad logic without becoming the same physical object. Randomness explores. Feedback selects. Weights remember. Hidden layers abstract. Intelligence does not have to eliminate uncertainty. It can transform repeated uncertain exploration into an efficient causal structure for prediction.